and the wilderness. Now, a lot has been written about his concept. It's a very uplifting concept, and I get it. I understand the heroic and the romantic notion of a frontiers person. But a lot has been written, and I'm not going to boldly go there. Sorry, that's a joke for people who remember Star Wars. Star Trek. But I will point out that after 100 years, we have a bit more experience of the idea of frontier thinking and frontier practice. And this lady is a professor at Umeå University in Sweden, and she's written an extremely good book on frontier thinking. And I recommend it to you. It's actually freely available from Routledge as an ebook, and I really recommend reading it. The point she's making is that she gets Turner's view as well, but there are times when frontier thinking is applied when it's no longer applicable. And that leads to unsustainable behavior, and it leads to actually rather irresponsible behavior. And for me, I'm not sure that I do think of space as a final frontier. In fact, I don't, because we're already there. We already use it, and we use it a lot. Now, this is a list of applications of space, and it's far from complete. I'm not going to go through them one by one, but there's a common denominator there. They make people's lives better, and in some cases, they even save lives, okay? And the other common denominator is that they are all existentially in danger because of space junk. They are all threatened. So for me, space isn't the final frontier. We're already there, we're working with it. And frontier thinking and practice is not really a good way to go. We need to think of it as a valuable and very fragile resource. Okay, now to explain what space junk does and is like, I have to talk about hypervelocity. Okay, it sounds like I've gone back to Star Trek again, doesn't it? Warp factor and all that. But actually, it's a real concept. What we mean by it are velocities more than 3 kilometers per second. So let's just compare that to things that you might know. Absolutely flat out, a Grand Prix Formula 1 car will reach 1/30th of that velocity threshold. Okay. The fastest jet fighter gets to about 1/3 of that threshold, okay? And even Mark Cavendish only doesn't exceed that threshold. He gets up to 150 cavs is actually the threshold for hypervelocity. My point is that hypervelocity is something that is outside our experience, our everyday experience, our worldly experience, and that's an extremely good thing, as you'll come to appreciate. But we don't know what hypervelocity is like. Because hypervelocity impacts are incredibly damaging, okay? Now, I did actually see a road sign like this when I was traveling in France, and the point it is making is that the energy you have that would be dissipated in a collision goes up as your speed v, but not linearly, it goes up as v squared. Okay? So it was a safety warning. They obviously don't have relativistic cars in France because this is a non-relativistic equation, but it still applies to hypervelocity. Now, in near-Earth space, what we call low Earth orbit, we can easily get relative velocities of 18 kilometers a second, well into the hypervelocity range. So what does that mean? Let's take an ordinary everyday object like a grain of sand, 10 milligram grain of sand, and plot its energy as a function of that velocity. And you can see when we get up to the top end there, it's considerable. In fact, it's more than the energy of a bullet fired from a high velocity rifle. okay, a grain of sand. And it does damage in space. These things look like they've been hit by bullets. They've actually been hit by grains of sand. These are panels, solar panels that have been in space. And this one on the right here is actually one of the ones from the Hubble telescope that was taken away and brought back to Earth when the telescope was refurbished in 1993. And you can see these, what are effectively bullet holes in it. Incidentally, there were two panels. The other one was so warped that it couldn't be put back into the space shuttle. And so the astronaut here, who is Kathy Thornton, is actually literally throwing the other one out into space. It was the only thing they could do, okay? And so essentially this is a source of space junk. It's just a solar panel that was thrown out. One thing to bear in mind is how brave these people are. As I say, a grain of sand, if it hit her, would be like a high velocity bullet. A fleck of paint, 10, 100 times more massive, would be like a cannon shell hitting her, okay? So it makes being in space incredibly dangerous. And this is hypervelocity. And this is why it's good that we don't have any common everyday experience of it. Some people have, unfortunately. I'll come to that. Let me move on to slightly heavier objects. So in the top panel here, I have put, sorry, I can't see on the screen, so I can't use the pointer. The top panel here, I've gone to heavier objects and I changed the scale. So the bullet is hardly getting off the horizontal axis. A small washer for a very tiny bolt, 0.3 of a gram, 5 of a gram, still reaches an incredibly large imaging. And the red line there is a cube of aluminium, 1 centimeter by 1 centimeter by 1 centimeter. So an aluminium sugar lump, if you like. And that reaches an energy that considerably exceeds that of the highest energy hand grenade available. Okay? That's what hypervelocity can do. And if that hits a spacecraft, well, I'll show you what happens in a bit. It's interesting, actually, because the expression that's become a political mode of operating nowadays, move fast and break things, actually came from a frontier man, a modern day frontier man. It came from somebody at the cyberspace frontier. It's actually was coined by Mark Zuckerberg. And for many years, it was the Facebook motto, move fast and break things. It's almost a definition of hypervelocity. Okay, so let's get rid of some things that I'm not going to talk about. These are some places where we can place spacecraft slightly away from the Earth. L1, for example, is where the gravity of the Sun and the Earth balance out, and we can put a spacecraft in orbit now. It's not stable, we have to work at it, we have to use a bit of propellant to keep it there, but it's very useful for science because we can monitor the Sun and we can monitor what the Sun is throwing at us. L2 sits at the other side of the Earth, and that's great for astronomy because you can look away from the Earth and away from the Sun, and that they're both sources of noise for astronomers, and that's a great place. And the James Webb Telescope is in orbit around L2. Why? I'm not going to worry about it. Firstly, there isn't much hardware up around these Lagrange points, as they're called. And secondly, when they're finished and we want to get rid of them, it only takes a small amount of propulsion, what we call delta V, to actually move them onto a trajectory. We'll take them in to burn out at the Sun. So they're easy to get rid of. So I'm not going to worry about these parts of space. But it's all different when we come down to near-Earth orbit. Now, there are lots of different ways you can orbit the Earth. There are 6 different parameters that describe every orbit. I'm not going to go through them all or talk about them. I'll just point out that one of them is the ellipticity, and orbits can be quite elliptical in shape. And what happens with apogee, when you're a long way away from the Earth, it's moving very slowly, but then it comes down at perigee, where you're closer to the Earth, closest to the Earth, and it swings by much faster. The other thing I want to just mention is the inclination here. This is the angle that the whole plane of the orbit is making with a reference plane, and we quite often use the Earth equatorial plane. So an inclination of 90 degrees, the satellite is going to go over both poles repetitively, whereas an inclination of 0 is one that's going to stay in the equatorial plane. Okay, let's So I'm now actually not going to worry even about the electricity. I'm going to get rid of that, and let's make it really simple. Go to a circular orbit in what we call low Earth orbit, which is not that high up. And I'm only going to use one equation in this talk, I promise, but it's a very simple one, and it's amazing the amount of physics relating to space junk that it covers. And it's essentially the equation for circular motion. You may remember it. Essentially, what you need is the gravitational attraction of the Earth on the satellite to supply the centripetal acceleration that you need to keep things flowing and moving in a circular orbit. So that's for circular motion. And we can actually then expand that a bit because we know the centripetal acceleration is mv squared over r. Some of you may remember that from school. And then the gravitational force given by Newton's equation. I can divide both sides of that equation by the mass of the satellite over r, rearrange it a little bit, and I get this equation for the velocity. And it has a very interesting property because as the orbital radius gets smaller, r, the velocity goes up. So the closer you are to the Earth, the faster it goes. And then you can ask the question, what actually happens if we slow the spacecraft down a bit? Okay. So the first thing we're going to do if we slow it down a bit is we're going to reduce this term a little bit below this term. So there's going to be a bit of excess gravitational force that will pull the spacecraft to a lower altitude. Paradoxically, it will speed up. So you've slowed it down and the darn thing speeds up. What's happening is actually it's coming down. It's not that magical. It's coming down in potential energy by falling, and so it picks up kinetic energy by increasing in velocity. So you end up with a spacecraft at slightly lower altitude, and it's always going to be slowed down a little bit because even at very high orbits, there's a little bit of atmosphere left. It's a very good vacuum, but there's still some atmospheric atoms and molecules to collide with, and they will exert a frictional drag on the spacecraft and slow it down a little bit. And once it's dropped a bit, because it's been slowed down, it meets a slightly denser atmosphere, and so it's going to be slowed even more, and it's moving faster, and the frictional drag goes as the velocity squared. So the thing is going to spiral back down to Earth, like I hope that little dot's going to do. And when it actually gets to near the surface, it will either hit the surface or more likely burn up in the lower atmosphere. And all that's come from that one simple equation, that understanding of how orbits decay. And we can let it decay naturally because it will collide with the atmosphere, or we can give it a push down. We can slow it with, if we've got a bit of delta V left on the rocket, we can slow the thing down and it will drop. And that's what we call deorbiting, where we deliberately bring the satellite out of orbit. We can put some numbers in for that velocity by putting the gravitational constant, the mass of the Earth, an altitude of about 700 or so kilometers. I get 7.5 kilometers a second. So if I have a head-on collision, that's 15 kilometers a second. If I've got a slightly elliptical orbit, it'll be moving faster at perigee. I can easily get collisions at 20 kilometers a second, which is, and I used 18 spots that I showed you. So that's just proving that we really can get these massively high velocities in collisions in space. One other thing that comes out of that equation, the time, the period of the satellite. It's got to go around 2 pi r, that's the length of the circumference, the speed vs. Put it in the equation for vs, I get this. And for a normal satellite altitude of, say, 800 kilometers, that's about 90 minutes period. But if we go out to 6.6 Earth radii, the period goes up to 24 hours. And that's what we call geostationary. If we're in equatorial inclination, so in the equatorial plane, we call that a geostationary orbit. And what's going to happen is the spacecraft is going around at the same velocity as the Earth underneath it. It stays over the same point. That is incredibly useful for lots of applications. Broadcast, for example. And that's why there are an awful lot of geostationary satellites. Geostationary ring at 6.6 RE from the Earth's center is incredibly crowded, incredibly full of defunct junk old satellites, as well as operational ones. The satellites there are less than 100 kilometers apart, which is pretty crowded, and it's getting more crowded because it's so useful. Okay, so geostationary orbit is something we do have to worry about, as indeed we do have to worry about low Earth orbit. So we have these three kind of all near Earth orbits that I want to talk about. Geostationary ring at 6.6 RE. We have low Earth orbits that are nearly circular. And we have these mid-Earth orbits, MEOs. A high inclination one, we use those in science, space science a lot. They take us up to an apogee well away from Earth, and then swing by very fast and perigee. And then we have mid-inclination ones, halfway between equatorial and polar, and they're very useful. There's what GPS uses, for example. Okay. And we've got to think about the space junk and how we deal with it for each of those. Right, so where does space junk actually come from? Okay, well, one of the surprising things, well, not surprising things, is collisions. Okay, given they're moving at these hypervelocity velocities and how big the energy that is, I've shown you that spacecraft colliding together, or even if they're operating or if they're defunct, or even debris bits hitting spacecraft is going to do an enormous amount of damage. Okay, so collisions between spacecraft. There are other things to collide with, like leftover rocket stages and fuel tanks, and there's all sorts of other junk up there. But actually, spacecraft can blow themselves apart and frequently do. And this is because there can be leftover fluid in a tank that vaporizes, the pressure builds up and it explodes, or deteriorating batteries cause explosions. So they can actually just destroy themselves. There's other sources of dangerous junk. If you vent fluids and gases, which spacecraft often do, it freezes, and that ice is incredibly dangerous at hypervelocities. There's weathering of spacecraft by just dust, wears off flecks of paint, and I've talked about even flecks of paint are extremely damaging at the speeds that we have. Micrometeorites and meteorites, although meteorite collisions with spacecraft are incredibly rare, but it's possible. Tools dropped by astronauts on spacewalks, it's very rare, but it's happened. And I'll talk about that in a bit, actually. And then deliberate destruction of satellites in what we call Star Wars tests. Now, I know of two of those. There have probably been others, but they weren't. There are two ones that are very significant, which I'll talk about. And then lastly, we have publicity stunts. Incredibly rare, but totally unnecessary. Okay, so why add to the problem? This is a movie. I'm going to show you three of the incidents. They're made by Easter. They're all completely realistic. The first is an explosion of a defunct satellite. It's falling apart, and then one of the tanks explodes. The second is a satellite that's damaged by a small piece of junk, and by that I mean a centimeter across, moving at a hypervelocity. And the third is a satellite that is completely eviscerated by a medium-sized bit of junk, by which I mean 10 centimeters across. Okay, so let's run the movie. Don't blink, because it happens incredibly quickly. Okay, so here's the first one. Very old defunct satellite, and bits are falling off it, I think. Yeah, there goes a bit. And then a tank explodes. Okay, and lots of junk everywhere, going off, able to hit other things, and completely out of control now. The second one, again, don't blink. Watch the solar panel on the left. There you go. Okay, again, irreparable damage to the craft, and it's out of control. And this one, this is a 10 centimeter bit of junk, and it's gone. Okay, I mean, it's completely eviscerated. That's what hypervelocity does, and that's why it's a good job that we don't have any understanding of how damaging it is. Junk that we get out of all this, we can classify. Below 1 centimeter, we call it small, and we estimate there's something like 130 million bits up there. These are slightly old numbers now, probably about 2 years old. And there's dust as well, and there's all sorts of things that can come into that category. There's medium, which we count as 1 to 10, okay, centimeters in size. And we think that there's about 1 million of those as our best estimate. We don't really know. Okay. What we do know is larger than 10 centimeters, which we call large, because we can track them, and we do track them by radar. And we think at the moment there are 37,000 known bits of debris of that size. But unfortunately, it doesn't stop there, because there is huge junk. This is the largest bit of space junk we know. The next largest bit will be the space station when we stop using it. This was ENVISAT. It was an Earth observation satellite. It was put into orbit at about 800 kilometers. On Earth's surface, it weighed 8 tons, and it's as big as a coach. So these guys working on it underneath it were actually pretty brave, in my view. I wouldn't like to be working underneath an 8-ton coach, but there we go. It was launched in 2002, and it did 10 years, great service, and made great observations for a decade until it failed, and almost certainly because it was hit by a bit of space junk, which rendered the whole thing as space junk. It was uncontactable after that. And it's still there. In fact, it will take 150 years to decay away and re-enter and hopefully all burn up in the atmosphere. And you might say, well, okay, let's not worry about that for now. 150 years is a long time. It's not in my lifetime. But actually, we still have to worry about it, because twice a year, a large bit of junk or still a defunct satellite passes within 200 meters of it. There's going to be a collision soon, and that will release a whole load more junk. So we do have to worry about it. And this is a great candidate for what we call deorbiting, trying to get the thing down in a safe way. Okay, I'll come back to deorbiting. So how much is there? Okay, well, this shows you all the objects we know in space in black. The actual working active satellites are in blue, and you'll see a big increase in recent years. This is the commercialization of space. A lot of these are Starlink satellites, and they reflect in the total here, although the amount of debris has also gone up. I want to just concentrate on these 2 leaps here, these big leaps in the total number of objects, and they're mainly debris. So it looks like something broke up. Okay. And actually, Phil alluded to this. I had a lot to do with the building of this radar in the planning and the management of the build. It's on Svalbard, which is halfway between the North Pole and the north of Norway. Wonderful place if you get a chance to go there. And soon after we got it working, it was mainly for studying the upper atmosphere and the aurora in particular. But we were also monitoring space junk, and we pointed to the north to do so. And we would often see this sort of thing. So lots and lots of space junk objects here. The red is moving away from us, it's redshifted, the blue is coming towards us, and lots of both going on, and a few that are moving at 90 degrees to the radar beam that are in green. So that was normal. There's several days of data there. And then all of a sudden, that changed to this. And what we were seeing every day was a burst of stuff going away from us, and then a burst of stuff coming towards us. So a lot of head scratching. And eventually, we worked out that we could work out what the orbit of the source of the junk had been. And we tracked it down, and we worked out that it was, I've gone 2 slides. Okay, so, no, sorry, I do need this one first. This is look at the radar looking north, and we're seeing stuff coming at us. But then later on, the Earth has rotated, and the band of junk is in the same place, and we would see it going away. And so we worked it out. We could work out from the orbit and how high the bits of junk were, from the range of the radar pulses, we could work out the height. And we eventually isolated this as the cause. The defunct Chinese meteorological satellite, but Pengyung IC, and it had been at 865 kilometers altitude. But actually, we didn't get there first. The people that look into this thing for a living got there before us, and they knew exactly what had happened. And that was on January 11th. The Chinese military had, in a Star Wars test, sent up what's just a solid missile. It's called a kinetic kill. A large delta V makes it head on to destroy it. Okay. By a couple of months, we catalogued over 2,000 extra fragments, and it's a lot more than that now. Okay. And it has consequences. In 2013, a small Russian satellite was hit by one of the bits of debris produced by that Star Wars test, and it made it space junk as well. So we've got space junk making more space junk, basically. It was a massively irresponsible thing to do. And it wasn't really a Star Wars test. The stupid thing is that they knew very well they could do it. It was just announcing to the world that they could do it, okay? It was political posturing. And I'll show you why it's so responsible. I have to add that it wasn't the first one. The Americans had taken a satellite out from a lower orbit, and the debris would decay away faster from a lower orbit, and that had been launched from a fighter plane. So to look at the consequences of that, this shows you if we just leave debris there and we have no way of doing anything else for the time being, how much it will decay in 100 years. And that's the predicted decay curve. Not even down to 80% of the present junk level in 100 years' time. Okay, and that's why I call it responsible. You'll notice it's not a smooth descent, and that's to do with the solar cycle, and I'll come on to that. Okay, so less than 20% of it will have decayed away in 100 years' time. Okay, and that's what we're dealing with. This junk is incredibly difficult to take away once it happens. What's the second one here, this step here? Well, actually, this was just an accident. It was two satellites that happened to collide. It's going to happen. It's getting very crowded up there. It was an Iridium satellite, which is one of a large polar orbiting fleets like this. It was actually number 33, and it happened to meet a Russian craft. And if I run the movie, you can almost see from this movie, it's almost like an accident waiting to happen. So here it is, quite happily doing what Iridium satellites do. And I've forgotten what Iridium satellites do actually for the time being. And they met. And that is a simulation based on radar data of the actual jump clouds. Okay, so here we see a collision again, and I think it's going to do it a third time for us. And you can see how the cloud actually spreads out. Some smaller bits are slowed down faster than large bits. But they generally just become part of the general mess of other spacecraft, defunct spacecraft, bits of space junk that are in low Earth orbit, and it's going to show you those in green. Okay. So it just becomes part of this incredibly crowded, yet unbelievably valuable bit of space that we call low Earth orbit. Right. We've seen what hypervelocity can do, so isn't this dangerous for the space station? The answer is yes, it's existential for the space station. The space station has what we call a Whipple shield. It's a series of baffles that slow things down enough so that by the time they hit the space station itself, the object is just splatted out on the wall. But it only works for objects up to about a centimetre in size, okay? And there's plenty out there that's bigger than that. And so the only thing you can do is dodge them, okay? And there are manoeuvres that are made to avoid space junk. And the number of them is actually shown here. It's increased over time. It goes up and down with the solar cycle. Again, I'll explain why in a bit. But the number of manoeuvres needed to dodge the junk has gone up. Okay. And remember, there are people on board. Why we really worry about all this is something called the Kessler syndrome. Now, all right, it's only a theoretical prediction of a space junk catastrophe. It was proposed in '78 by a NASA engineer called Donald Kessler. And it's basically runaway space junk, where debris from one collision causes other collisions, that cause more debris, that cause other collisions, and so on. Okay. Now, we have models of it. This shows actually a relatively simple one. Okay, and it shows all the interactions between different sizes of junk and the sources of junk. The rings that are in B are of no consequence in that they are neutral in terms of the amount of debris produced, but the rings in red are actually positive feedback loops. They're where bits of junk produce a lot more junk. And overall, they're positive, and the whole thing is driven by the number of satellites you're putting up, because that determines the amount of raw material for producing all this junk comes from. And all we have to counter it is orbit decay. So these are negative feedback loops that actually work to reduce the amount of junk. But you've seen how slow they are compared to the rate that we're putting stuff up. So the predictions are absolutely unambiguous that we are heading for a Kessler catastrophe, unless we do something about it. There isn't really any serious doubt about that. It's inevitable. And this would make space missions and all those benefits I talked about impossible, because you put a spacecraft up, it would be immediately hit by junk and destroyed. And it would make space travel impossible. For those that still like the frontier idea, it would be like living in a cage, because you'd be able to see for deep space, but you sure as heck wouldn't be able to get there, because you try to go through the junk layer, you would get hit. So it's like putting a cage around the Earth if you're really into the frontier way of thinking. And it would stop us getting to the frontier, not help us. So what can we do? Okay, how do we mitigate this? Well, it depends where we're talking about. I'm not going to talk about deep space. I've said I'm not worried about that. GEO, we have a strategy. What we do when a spacecraft's nearly dead, while it's still got some propulsion left, while it's got a little bit of delta V, we move it out to a higher orbit. We call them graveyard orbits. And we let them sit there. We hope if they explode or collide, they don't send debris back to geostationary and damage the satellites that are still working in geostationary. So that's at least one mitigation strategy for GEO, geostationary. But for low down, it's more difficult. Okay, we don't have a strategy for where we're putting our sat-nav satellites at the moment. We just hope it's not that crowded, but it's a worry. We don't have a strategy. And in LEO, low Earth orbit, all we have is deorbiting. Okay, so we can let that happen naturally. Problems with that take time, for one thing, but there are other problems. But we can also make it happen. If we apply a bit of delta V and slow the thing down, it will start the re-entry procedure. And we could do that in a controlled way. And that's important to explain why in a bit. But this is a cleanup mission called Remove Debris, which is actually a UK mission, and it used a net to collect a bit of space junk, and it worked. And then you can tow the thing, you can slow it down, make it drop, let it out the net, and it will burn up. So that was actually a successful bit of clear up using a net. There are other proposals. The ESA one here is clear space, and that is to use tentacles to grab something and do the same. There's an idea that we could use magnet that would pick up magnetized metal junk. But of course, that's not all magnetized metal. And then other bits, there's talk of using harpoons to harpoon it and drag it down. Okay, so there are proposals, but they're very much in their infancy at the moment. And this is getting a bit urgent. Now, you may have seen on the news, but this is a ring. We're not exactly sure whether it was between rocket stages or whether it was between satellites that were being launched to geostationary. It fell in Kenya, just outside a village. There's been doubts, because it doesn't seem to have much charring. There has been doubts if it really is space junk. But on the other hand, it was red hot when it was first found. And all around it, bits that are definitely space junk have been found. So we're pretty sure it is space junk. We don't know where it came from. All the space agencies are denying it's theirs, and nobody seems to be able to or want to identify it. There was talk that it could have been from an Ariane 5 launch that put 2 geostationary satellites up. That would kind of fit. Ariane deny it, says it doesn't look like anything of ours. But if that's true, that launch was it was 18 years ago. So this thing's been up there for 18 years waiting to drop on a village in Kenya. There have been other examples. There's a family now living in Florida who are suing NASA because a bit of debris destroyed their house in California. It came through the roof, it went through the first story, it went through the second story, and made a big hole in the ground underneath the house. It missed their young son by a matter of meters, and the father was in the house at the same time. And it turned out to be a battery that was jettisoned or dropped or whatever, broke off the space station. So they're suing NASA in what is a very interesting test case of culpability here. SpaceX junk has fallen on North Carolina and in Canada, okay? And it has been identified as that. And in fact, Qantas have been complaining about SpaceX junk to the extent that they've cancelled flights in the Southern Hemisphere because of it. And then recently, the loss of the SpaceX rocket meant that all flights in the Caribbean area had to be diverted because of the danger of stuff falling out the sky. So this isn't just the space problem. Some bits will survive and not be burnt out and make it through to the surface. It's a worry. Okay, right. The last thing I have to explain is space weather events. They do wonderful things like giving us aurorae over well-known places in the UK, as we've had in the last year. But they also heat the thermosphere, and that's what this movie is about. It's a simulation of the coupled ionosphere-thermosphere system. It's showing the temperature, I think, at about 400 or 500 kilometers altitude. You see the heat being deposited near the poles in the auroral oval, but then the heating spreading around the globe. And that means it's going to slow down everything in lower orbit. It will make smaller bits of junk deorbit quicker, and it will cause others to start the spiral into re-entry. So these events we work quite hard at trying to be able to predict them and trying to predict how much they're going to heat the thermosphere, but they happen very quickly. And I'll show you a consequence of that. Right, I've put all that. Right, and of course, for the satellite, the things like the space station, it has enormous implications because you thought you knew where everything was orbiting, where all the junk was, and suddenly it's all rearranged by this heating event of the upper atmosphere. And the events like this get more common at sunspot maximum. Now, this was an interesting example. This was Skylab. Skylab was always intended to drop in altitude, and then they were going to use the shuttle to push it back up again. But the shuttle was delayed, and the solar cycle turned out to be more active than they predicted, and so the orbital decay was more than they predicted. And there was nothing to push Skylab back up, and it re-entered, fortunately landing in the desert in Australia. But at least the core of it, bits will have fallen off before then. When something re-enters, we go through a process rather like this. The solar panels are stripped off first, and we get small debris falling, and then the main thing starts to break apart, and we get debris from that breaking up. And then the core of it, the really large part, which will probably burn up in the atmosphere, but might make it through to the surface, forms the primary debris. So we get this trail of debris along the orbit. And what we want to do is to make that debris trail as short as possible, okay? And also over unpopulated areas. Now, only 3% of the Earth's surface is populated, so the chances are quite good, but you're courting disaster. Sooner or later, it's going to land on if it's uncontrolled like Skylab was, it will land somewhere. And the only way we control it is to use some delta V to initiate the start so that it falls in a place that's safe. So we initiate it at a time so that it falls somewhere safe. The problem is, if the thermosphere suddenly heats up, all your calculations will go out the window. Let me show you an example. This is a cold thermosphere profile in density, and this is the density of a hot thermosphere. Okay, so solar activity has heated the red one, whereas the blue one is the cold one. And it goes between the two on a range of timescales and can go quite quickly. These are the orbits. Okay, so if this is the red one, it descends faster and re-enters. Everything below about 190 kilometers is effectively re-entered. It's not in orbit anymore. It's going to fall almost straight down. But look how much longer, oops, sorry, come back. Look how much longer it takes for the cold thermosphere to do it. And that time gap is about 5 orbits. So if you're trying to get the thing to come down in the right place over an unpopulated area, you've got to know the state of the thermosphere. And so you've got to predict the state of the thermosphere very accurately. Otherwise, you're not going to get the thing to descend in the right area. We've known this science for a long time, since the very first satellite, which was Sputnik. Sputnik didn't do anything but tell you that it was there. It just went beep. And it was basically a message to America saying, hey, look what we can do and you can't. And there's no other instrumentation on it at all. But we could monitor its orbit by orbit. And what we found was that the orbit period would go up after one of these geomagnetic heating events. This AP index is an index of geomagnetic heating, the thermosphere. So we've known this heating effect for a long time and got to understand it quite well. How am I doing on time? Okay, too much time to stop. I should talk a little bit about Starlink. Starlink is a commercial internet provider on a global basis. The first launch is in 2019. There are now over 7,000 of the things in orbit, and it is planned to rise in the near future to 12,000, and they're even talking about 34,500 in the end. This is a heck of a lot of new satellites. There are about 4 million subscribers. SpaceX are very coy about who they are, but we estimate that about 25% of the use is military. There are other rivals, but not as extensive as Starlink in a plan. Now, they have autonomous motors on board, and this is where, surprisingly, I'm going to be talking about a responsible side to SpaceX. Because those motors are used to get the things up into their operational orbit. And they're also there and available for end-of-life deorbiting. So they can be brought down at a safe time, at a safe place, and burn up in the atmosphere, well away from centers of population and in an area where airlines know not to go. And the propulsion is also used for junk evasion. So it sounds a bit like a solution. And at the moment, the input for that comes from the ground-based radars run by the American military, and they send up the information of where the junk is, and they maneuver around it. And I think they've done nearly 7,000 maneuvers so far to avoid junk. They want to make that autonomous so that they spot the junk themselves and move, but that's a nightmare for everybody else, because one of the good things about junk is it tends to stay in the same orbit as the thermosphere heats up. And so if this stuff's moving around on its own in an unpredictable way, it's really bad news for everybody else. I should just mention it's an absolute pain for astronomy. The reflection of light off the bottom interferes very seriously with ground-based astronomy. And even more serious is the radio noise they're producing. And we have major new radio telescopes like LOFAR and the Square Kilometre Array, which are seriously compromised by the radio noise. So it's bad news for astronomy, there's no doubt about that. The way they launch Starlink is really interesting, and again, rather responsible. What they do is they take it up, there's a stack of 30 of them, by the way, there. About 20 have already been released. So they take them up stacked like chairs in a canteen, and they release them one by one at a very low altitude. And it was, I think, about 210 kilometers before an event I'm going to talk about. And then they test them out at that low orbit. And if they fail any of the tests, it's very easy to deorbit them from there, which is what makes it a nice, responsible procedure. And if they're okay, they send them up to their operating altitude of 530 kilometers. But it was risky because, for example, on February the 3rd, 2032, they launched 46 and lost 38 of them because all but a few had not been elevated before there was a geomagnetic storm that warmed the thermosphere and brought the others down. Unfortunately, SpaceX then decided to raise that altitude, which doesn't entirely negate the responsible way of doing it, but it's a pity because the way they were doing it was quite a good way of minimizing the space junk. There's still all the rocket stuff. And this was film that the Astronomical Society in Puerto Rico captured of the first of those satellites coming down. I won't show you much more, you get the idea. They saw them coming down from Puerto Rico. Okay, so let me finish up. Space is an incredibly valuable resource for us. We use it all sorts of ways, but it's also very fragile and it will not survive irresponsible use. So we have to exploit it in a responsible way. And our future use of space is threatened. This movie here, each one of these dots is a real tracked object. The size of them has been exaggerated for effect, but nevertheless, you can see just how crowded lower and dangerous lower Earth is getting with so much object moving in all different directions. Okay, so that's my take on space junk, and that is why we need to talk about it. We need to talk about it, and we need to do something about it, or we are in trouble. Okay, here we go.
We're going to do Q&A now. So if you have any questions, if you want to help Sam's here, you can help as well. Oh. That's all right.
Really sorry for folk at home, but because I couldn't see the screen, I couldn't use the pointer.
I know, we're going to get that sorted before the next.
I'm so sorry if you were thinking, which bit are you talking about? I put the pointer up on the screen in the room, but that doesn't help you at home. I do apologize.
Any questions? Good. So just make sure you can use the mic when you have a question. Thank you.
Hello, thanks very much for the call. I have a comment and a question. Can you hear me?
Yep.
The comment is, from memory, I always believed the first anti-satellite test was back in 1962, the Explorer 6.
You could well be right. My 2 was the 2 that I could actually see on that graph. Okay. Okay. You could well be right. So I did actually, when I put that, I would have put 2 that I know of, but I'd run out of room on the slide. They're the big 2 that have actually caused the jump, but you could well be right. Yeah. I just mentioned the American one because it's very easy to be critical of China for the Fenyang IC thing, but you know, the example had been set. So,
how feasible do you think it would be for a rogue regime or some environmental group to set up a Kessler bomb and actually deny humanity access space deliberately?
That's an interesting question. I don't actually know, and I don't think we know, because I don't think we know just what is the critical point where everything starts to destroy everything else, basically. I don't think, although the models tell us that it is inevitable, we get to that point, I don't think we accurately quantify what that point is. So my guess is it would be a little bit like the Fenyang IC. It would produce a heck of a lot of junk. It would generate problems. It would make the problem worse. Probably not tip us into a Kessler event. That would be my guess. But I don't know how close we are. Okay, I just know it's because you have these launches. We have more launches than we've ever had, and they're driving all those positive feedback loops. We only have deorbiting At the moment, that's all natural deorbiting. We're not doing any of the planned cleanup missions. And for the big stuff like the space station or Envisat, we probably will manage to use some delta V to slow them down and make them drop in the right place, assuming we get the thermosphere predictions right. But the rest of it's just going to come down where it will, like Skylab did. They were very lucky it landed in the, well, they're not very lucky, only 3% of their surface is populated. So chances are it will land in an unpopulated area on one event. If you keep on doing it, sooner or later it will land somewhere you don't want it.
Okay, thank you.
It's a good question, Mother.
If there is a thing in lower orbit, would it propagate to geostationary, or would that be so a
No,
long way out?
no, probably not. No. I don't think so. I think our worry is more that the graveyard orbit could infect geostationary. But low Earth orbit there's a big difference between 800 kilometers up and 36,000 kilometers up, which is where geostationary is. So I don't think that is a concern, no. But they both have different concerns, as it were. We don't have good solutions for either. We have partial solutions and partial mitigations.
I was just going to go back to what we had a few months ago here about how we don't see alien civilizations. But it's a sort of sad realization that very soon every space race is going to get in themselves on their own planet. Yeah. Okay. So alien civilizations that have a very short window of spacefaring.
That's true. We never know, of course, if they're going to follow the same development curve as us. But like in the Drake equation, the probability of finding a tangent line, one of the factors is, can you survive your own atomic age? So can you survive having an atomic bomb? And does every civilization?
Everyone.
Yeah. No, then they wouldn't get out. No, I know. Did anybody see the message that Jimmy Carter left on Voyager 1, by the way? It's brilliant. There's a line in it where he says, "We are trying to survive our own age so we can exist in yours." Because he knew it billions before the message reached everybody. It's just great.
We're talking about people from Germany and Australia.
Oh my goodness.
I just want to know, there's a question from online that asks a couple of questions here. Curious about office with that person in the state. Office, I'm assuming that's something you mentioned in the talk. Maybe it's missed out, but I'll check in with him.
Yeah,
and then,
sure.
Do we see for the line very obvious constellations? Talking about the Betelgeuse, would that affect things?
It could do, but actually probably through their electronics. It's probably a matter of loss of control from something like the electromagnetic flash actually affecting the electronics and things like that. So it could do. I don't think a shock wave or anything like that would propagate, and it would take. Well, yes, we would have a lot of warning. But the electromagnetic stuff could come relatively quickly, and that could interfere with the electronics. And if you've lost control of the satellite, it becomes junk. It's just junk.
One of our attendees on Zoom asked, what's the best or effective way to overcome this? Which isn't anything we can answer. And also, what is the current estimate of time we have for runaway catastrophe?
Okay, that's a bit like the question we had before. The answer is I don't know, because I don't really know how close we are. The inevitability of it, I don't think, is in doubt. The timescales are. And I have to say that I'm quite proud that the one deorbiting mission that has successfully done something so far is the UK debris mission. And that uses a net, but it's not going to pick up all the little bits, and it's going to but you could get some of the bigger chunks out. And bigger chunks make little chunks. That's the problem. Yeah. No. Yeah.
We definitely have questions on YouTube, so if you have any questions in here, I'll ask speaking event.
Now, Max has done a whole display on this subject, so I'm waiting for this question with trepidation.
Yes, right, thank you. Yeah, let's just go back to your question. I don't know about that question, comment really, and Professor and he was in university. Every day.
Yeah.
So different things.
Yeah.
So somebody's got to prove even the other.
Yeah.
Down.
Yeah.
And also there's the elevation of the apparatus.
Sorry. Yeah, no, I really should have mentioned that. It's the sheer volume of what's going to have to burn up in the atmosphere is already affecting the stratosphere. We're getting metals in the stratosphere that never used to be there. And we have no idea what the effects of that will be. For example, the ozone layer. The ozone is quite important climatically because it absorbs ultraviolet, and we really don't know what the effects of that are. So that's an extremely good point. I did have it on the slide, but I forgot to mention it. Yeah. Oh, and on the rate, at least the Starlink satellites can do it themselves. So if Starlink is still employing people who have the skill to do it, they have the delta V and the propulsion to do it. And so they could probably do quite a lot of them at a point, but whether they can do them every 15 minutes, I don't know. Not necessarily, as Kenya has proved. That was a half-ton bit of metal that may have been in space for 18 years waiting to drop out.
So we have a couple more questions on YouTube. We'll do the two question. The questions that I find YouTube are around basically
Right.
we're doing all these launches. I would know who's launching by
The whole area of space